So hello everybody, I'm Carolin and today I'm presenting my paper entitled Freeze-Thaw Durability of Glass and Basalt FRP Rebars, which was written as part of my research work at the Lubeck University of Applied Science and in collaboration with the Lubeck Materials Testing Institute in Germany. First I will introduce you the topic with the help of an introduction. Then I will discuss the experimental design and the materials and the methodological. I will then briefly present the results of the individual experiments, which will then be analyzed and discussed. Finally, there's a summary and a conclusion. Reinforced concrete is one of the most commonly used building materials and has established itself very well as a material for structural work in both the German and US construction industries. Although concrete and steel complement each other in some of their properties, the combination also has disadvantages such as the susceptibility of steel to corrosion. Fiber-reinforced rebars can offer an alternative that has the same positive properties as steel and is resistant to corrosion. These bars have a wide range of properties according to the current state of research. Many types of tests have already been carried out to obtain results for tensile strength, modulus of elasticity, durability, or chemical resistance. Frost resistant is another important material property that has not been the focus of much research to date. This is because buildings can only be preserved for decades if the durability of the bars under frost load can be ensured. Fiber-reinforced polymer rebars are a composite material consisting of fibers and a polymer matrix that encase the fibers as shown here. When the rods are manufactured using the pultrusion process, air pockets and micropores can form inside the rod. Water can penetrate the pores and freeze there. The freezing of water leads to an increase in volume of approximately 9%, which can cause further cracks to form and existing cracks to widen. As the number of freeze-thaw cycles increase, the damage can spread. The aim of this research work was to investigate the frost resistance of fiber-reinforced polymer rebars and to subject the rods to freeze-thaw cycles for this purpose. In this way, the durability of the FRP bars on the one hand and the retention capacity of the load-bearing capacity on the other are investigated. Fiber-reinforced polymer rebars made of glass and basalt, each with a diameter of 8 and 60 millimeters, respectively, were investigated. The rebars were provided by German manufacturers and therefore different from manufacturers from the USA. The following test matrix was used to carry out the test on the rods in order to obtain sufficient information about the test results in the discussion. The bars were divided into 3 test groups. The first group was not exposed to any freeze-thaw load. The other 2 test groups were placed in a water bath for a period of 11 weeks to allow saturation of any pores and defects. They were then placed in the freezer for 18 and 160 freeze-thaw cycles respectively. 3 different tests were carried out on the bars after the freeze-thaw cycles to obtain results on the material properties. Tensile tests, as well as tests on transverse shear strengths and horizontal shear strengths, were carried out, which are presented in more detail below. Before the tensile test to determine the tensile strengths could begin, anchors in the form of steel tubes had to be installed at the end of the test bars. These were filled with an expansion mortar. After a sufficient curing time, the bars were installed in the test facility and tested. During the tensile test, an extensometer was attached to the center of the bar to measure the elongation of the bar. Before the first fiber break occurred, the extensometer was removed. The rebar was loaded in the tension until a complete fiber break occurred. The following photos show the tensile test sequence. The third photo showed the first shearing of the outer fibers of the GFRP rebar. The last photo shows the end of the test after all the fibers of the rod have broken. The following photos show all samples of the test series with 0 freeze-thaw cycles on which tensile tests were carried out. It is noticeable that the fibers of the glass fiber rebars tear much more finely, whereas whole strands of fibers remain bundles in the basalt fiber rebars. It also happened with the glass fiber rods with a diameter of 16 mm that they were pulled out of the anchor and the fibers did not fail. To determine the transverse shear strength, the samples were clamped in an appropriate test sieve and punched through using a pressing blunt steel blade. The maximum force measured describes the shear force required to cause shear failure. The two image shows samples of two 60 mm thick FRP rods made of glass and basalt after failure. The third test carried out was the test to determine the apparent horizontal shear strength. Here, a 3-point bending test was performed at a short span, forcing shear failure in the horizontal direction and parallel to the fibers. The following photos show specimens with a diameter of 60 mm after failure. The parallel cracks at the end of the glass fiber rebars in particular are clearly visible. While the test bars, which were to be exposed to frost, were in the water bath, a saturation measurement was carried out in parallel. The results of the saturation measurement can be seen in the graph. All samples increased in weight during this period, but the basalt fiber rods significantly more than the glass fiber rods. The basalt fiber rods with a diameter of 8 mm did not meet the criteria of the saturation maximum and the 24 hours absorption limit. The fiber content of the rods was also examined. The investigation showed that the basalt rods had a fiber content of 78% and the glass fiber rods of 87%. Now we come to the results of the tensile and shear test, starting with the tensiles test. This graph shows the result of the specimens that were not exposed to frost. The basalt fiber rods are shown on the left and the glass fiber rods on the right. The rods with a diameter of 8 mm are shown at the top and those with a diameter of 60 mm at the bottom. It is noticeable that the glass fiber rods achieve a higher tensile test than the basalt fiber rods. In addition, all curves show a proportional increase until the maximum stress is reached, following by a drop. The samples of the individual groups show similar values to each other. The following graphs show the result of the same group after a frost load of 80 cycles. The results of the samples with 0 freeze-thaw cycles are shown in red. In the case of the basalt fiber rods, it is clear that the maximum stress values after 80 freeze-thaw cycles are lower than those that have not been subjected to freeze-thaw stress. For the glass fiber rods, almost the same stress values are achieved as for the samples with 0 freeze-thaw cycles. The following graphs show the stress-strain curves of the specimen during the tensile test, which were recorded with the extensometer. The modulus of elasticity of the FRP bars can be calculated from these curves. All graphs show linearity, whereby the increase is higher for the glass fiber rods than for the basalt fiber rods, which is why the FRP rods have a higher modulus of elasticity. The measured modulus of elasticity for the glass fiber rods was around 66,000 megapascal and 46,000 megapascal for the basalt fiber rods. The graphs of the samples after 80 freeze-thaw cycles show only slight changes in their slope compared to the previous samples after 0 freeze-thaw cycles. The calculated modulus of elasticity hardly changed. The results of the transverse shear strength test also show an increase until the maximum shear force is reached and a subsequent drop in the curve. Here, the glass fiber rods achieve higher maximum stresses than the basalt fiber rods. The bars, which were preloaded with 80 freeze-thaw cycles, show only slight deviation from the previous curves. The maximum value reached approximately the same level as before. The result graphs of the specimen tested for the apparent horizontal shear strength also show an increase until the maximum shear stress is reached. After that, the graph levels out and no further increase can be seen. The glass fiber rods achieve a significantly higher maximum value of shear stress compared to the basalt fiber rods. Compared to the bath with 80 freeze-thaw cycles, the maximum stress in the basalt bars is significantly lower. In the case of the glass fiber rods, this is only minimally lower. A clear drop cannot be seen. Now I will come to my analysis and the discussion. The following graph summarizes all the results of the 3 tests just presented, as well as the modulus of elasticity. The results were converted in such a way that the retention capacity of the tensile and shear stress of the FRP bars can be recognized. The orange line shows the summarized results of the modulus of elasticity measurement. Overall, the modulus of elasticity of all test samples did not change significantly. The green line summarized the results of the transverse shear strength tests. A drop in the retention capacity between 80% and 95% can be seen here. The blue line shows a significant loss in the retention capacity of the FRP bars. This shows the horizontal shear strength, which drops significantly to approximately 65%, especially for the basalt fiber rods. The retention capacity of the tensile strength is roughly between that of the transverse shear strength and the horizontal shear strength. Overall, it can be seen that the glass fiber rods have a higher retention capacity in all tests compared to the basalt fiber rods. Overall, it can be stated that the decrease in strength proves the formation of pores in the bars, which are due to the manufacturing process. Furthermore, higher saturation leads to greater strength losses. The reduction of the retention capacity is particularly evident in the basalt rods, which exhibited a high saturation in the preliminary tests. The test on transverse shear strength primarily examined the fiber properties. As the least changes were seen here, the fiber are not susceptible to frost. In contrast to the resin matrix, here the test for horizontal shear strength, which focused primarily on the resin properties, shows significant losses due to frost exposure. The decrease in tensile strength is therefore caused more by the poor resin quality than by the fibers. Furthermore, the production quality also plays a decisive role here. Better results in the properties of the fiber rods can only be achieved if the resin is evenly distributed between the fibers in the FRP rod. The modulus of elasticity show no change across all tests between rods with and without frost stress. This is rather due to the fact that the modulus of elasticity was measured by the extensometer at the outer edge of the bars and the damage occurred inside the bars. In conclusion, I will briefly summarize my presentation. A number of 228 fiber-reinforced polymer rebars made of glass and basalt with 2 different diameters, namely 8 and 60 millimeters, were tested. Some of the rods were aged through 80 and 160 freeze-thaw cycles. Tensile and shear strength tests were carried out to compare the frost age and virgin bars. In summary, it can be said that the freeze-thaw load leads to a reduction in the strength properties of the FRP bars. This is greater for the basalt rod than for the glass fiber rods. The resin matrix is more susceptible to frost than the fibers. The production quality of the reinforcing bars also plays a decisive role when it comes to frost resistance. The better the production quality, the better the tensile and shear strength properties. The frost load had no influence on the modulus of elasticity when these tests were carried out. Thank you for listening.